Again, thanks Marta for the introduction. And the plan today is to give you a little bit of overview how we use high energy X-ray diffraction for operando and in situ studies of electrochemical systems. So because we are just starting the remade projects, we don't have, of course, much results from the actual recycling of, let's say, batteries and fuel cells and other energy conversion and storage systems. But everything which I will show you here will be very useful if you're planning to measure anything at ESRF using high energy X-rays and using diffraction or small angle scattering, or maybe some other more complicated techniques which I will show as well, such diffraction microscopy or diffraction tomography. So let me move on here. So now where we are as a society is that we power our society through fossil fuels. You all know the issues with the fossil fuels. You all see that we haven't get the greatest skiing year in Grenoble because it was very warm. And the question is, why is that, right? So why we use fossil fuels? And now if you actually look here, but maybe I can do this pointer thingy. Yeah. So if you look at the energy density of the fossil-based fuels, you'll find that they're very dense to their weight or their volume. So this is the orange. So diesel and gasoline has both high volumetric and specific energy density. So that's it. This is an ideal substance to actually power our society. Now the problem is that when you burn fossil fuels, you generate CO2, which is definitely not good. So if you look at the, like if we have here like the plot about the possible actual substitutes for the fossil fuels, then you can look here and we can see on the left side, left corner, we can see what the batteries can do at this point, right? And you can see what the hydrogen does at this point. And batteries and hydrogen are at this point seen as a good approach to actually offset the CO2 emissions. So you can see that we're not doing really well, right? So our technology, if we are not talking about aluminum batteries or magnesium batteries, which of course are up and coming, then we see that the sodium and zinc and lithium batteries have really low energy densities, right? For both volumetric and specific. And this is not good, right? Because it's really hard. You have to make much more effort to actually get to the same point as the fossil fuels. Hydrogen has really high specific density, really low volumetric density. So that means that hydrogen is good for certain applications where you have to move the fuel with you, right? So if you want to send the rocket into the space, perhaps hydrogen is good. If you want to run the plane over the globe, hydrogen is good. If you want to run a car in the city, this is questionable, right? Now, the other problem is here, the efficiency, right? So even though the gasoline is not very efficient when we burn it in combustion engine, it is really high energy density, right? So now in the battery world or the hydrogen world, if you want to get to that, we have to really improve the efficiency. The other point is that we should do it in sustainable way, right? And this is what this whole project is about. So now we need new materials to really power the society, and we need to make them and recycle them in a way that we form the circular economy. So I will now, more focus in like, let's say 3 areas of this big scheme, right? So this is how our energy grid will look in 10, 20 years. So we have the fossil fuels still inputs. Fossil fuels are not going to go away, and I showed you why, right? You have the renewable energy input. They both go into the electricity grid. And then we will have something which is called hydrogen grid, which will be parallel to the electricity grid. And this will be used to either store the energy from the renewable sources or also to make precursors for our industrial processes. So in between, you have, this, let's say, interface where you have to convert the hydrogen to electricity and electricity to hydrogen. Okay, so now we are getting into the electrochemical conversion systems. So, and it doesn't matter if we talk about batteries, fuel cells, electrolyzers, some kind of flow hybrid batteries or whatever. The idea is pretty much the same, right? So you want to combine two electrodes, where the electrons have different electrochemical potentials, and you need to connect them with some electrolyte where the ions can freely move. And then you harvest the electron from one electrode and you run external load, and then you move it to the other electrode where the electron has different energy. But this process is actually quite complicated because first of all, you have to catalyze, you have to get the electrodes from your molecules or atoms, right? So that's the catalysis part. Then you have to move the electron in the electrode, so electron conduction. You have to move the resulting ions in the electrolyte and within the electrode, in the case of batteries. So this is ionic conductivity. And this, you have to do this in really large current densities. So the current densities are so large that there is no equivalent in nature. None of the organisms or anything we know can actually do the task in such a high current densities, what we can do and what we have to still improve. So in the left is the battery system, on the right is the fuel cell. MEA, right, is exactly the same idea, but instead of inserting the ions into the bulk of the material, like in the batteries, in the lithium or insertion batteries, as we call, then you actually have in fuel cells or electrolyzers, you have a stream of chemicals where you harvest the electrons from them, right? So there's lots of materials and engineering issues. And one of the issue is also that they need to actually work in certain environment, right? Otherwise, they don't simply work. And if you take them out of the environment, they typically work differently. So the characterization of these materials in a real sample environment is really a key to understand such a complicated device. And of course, here, the correlative characterization in situ and operando and multimodal, like for example, in the remade projects where we combine not only multiple techniques, which can cover multiple length scales, but also different probes, which is a really unusual approach in this field and for sure for the recycling. But those things are really key to understand the processes in these devices, how to make the materials better, how to recycle them, and how to get into the actual process them, and how to get into actual circular economy. So at ESRF, we use now our new tool, which is called extremely brilliant source. So it's a new synchrotron, which has much higher brilliance, much higher coherence. We can achieve coherence and brilliance at much higher energy. We have much smaller emittance, and we have much higher flux. So this helps us in all these tasks. So this machine is built for this kind of characterization where you need really high spatial resolution with maximum speed, and you want to ideally use multimodal approaches. Okay. So now, at ESRF, we also use different instruments. And I think most of the instruments which are here on this list are available for remake, which actually spans on all the length scales which are needed for the characterization of energy conversion and storage materials and devices. So if you look here at the top part, right, so you can see that to actually optimize the fuel cell, you have to first optimize the catalysis on the surface of the nanoparticles. So then you have to also optimize the size, distribution, and surface areas of the nanoparticles. Then you need to optimize the morphology of the catalyst layer. So we are getting into these diffusion length scales, right? Then you have to really optimize the whole membrane electron assemblies, MEAs, right? So how they're put together, how they're connected, how the interfaces looks like. Then you take the whole thing, then you put it on single cell, right? And then you actually take those single cells, you stack it up into the stack, and this is something which goes into your car. And this whole length scale problem is in heart of the optimization of such device. The same exactly can be said for the batteries. Okay, so now if we look at different, and now we have this instruments which can work together, and we use it quite often, right? These capabilities that, for example, IDO1 is really good at looking at the nanoparticle and kind of mesoscale sizes, right, of nano objects. iodine 16B is the tomography beamline, which can nanotomography, which can also do the same scales, but now from different perspectives, right? Which is also very important. Now we have, for example, the absorption beamlines, ID26, which look at the atomic scale of the material, and ID31, which I will show the results from this particular beamline which we operate here. And Marta is a junior scientist at this beamline, right? And then we look at with the diffraction techniques, so elastic scattering techniques at atomic scale. And then I'll show you there is a trick that you can actually do tomography with scattering techniques, and therefore we extend the scales also to the level of MEAs and the one cell, let's say, levels. So, but in overall at ESRF, we can span the whole length scale of these programs. So now, why we want to use high energies? So that's important, right? And that's because we're specializing in these operando in situ experiments, which are complicated. And high energy probes helps us a lot because they have, first of all, high energy penetration. So it's very difficult to make real device where you have to miniaturize everything because your probe is not penetrating. So it's possible, but it's difficult to get to the same performance levels as the material would normally work in the real running battery, right? So, but with the high energy, you have enough energy that you can shine through single cell or even stack of the batteries on the beamline, and you can probe, therefore, the whole volume of the cell. So now the other advantage is that with high energies, you have compressed reciprocal space, right? So if you take your X-ray diffractometer in the lab, then with the copper K alpha source, then you probably have to measure a long time to get few peaks, right? So with high energies, we actually use these 2D detectors. We shrink the reciprocal space, so we can actually see the full the Becher rings, and therefore we have really high statistics, and therefore we can measure many rings very fast, which then helps us to do certain kind of experiments which needs time resolution or where we can need to probe the large volume of space. And then one important aspect of the high energy is the actual induced damage by X-ray, because the last thing you want to do is to take your probe, you shine on your material you want to study in certain conditions, and you find out that you are studying actually some different conditions which have been induced by the X-ray probe. So sometimes it's in form of the radiation damage to, for example, polymer materials, but sometimes it's actually just simply that you alter the environment to the point that your environment is not the same as it's supposed to be. So you're measuring the right system, but in completely wrong environment. So high energy helps you, especially for the diffraction, because if, for example, this black curve is the ratio of the cross sections of photoelectric cross section and the elastic scattering cross section, that's the blue line. If you put the ratio, then it goes up as a function of energy. That means that for lesser induced damage, you get more diffracted signal. So you don't need to actually expose the sample that long. Okay, so now this is our typical approach, if we can. So for example, ID31 beamline is built for this kind of approaches where you have source, right? Then you maybe focus the beam here. Now I think my mouse doesn't work. Focus the beam here, and then you have multiple detectors around, and then you check different let's say different ranges of reciprocal space. So for the small angle scattering, you put the detector very far away. For wide angle scattering, you put it closer. For the BCDI, you put it on the side a little bit. You look at one reflection only. And then we have also special new instrument, which is X-ray transmission microscope, which is equivalent of EM, right? Which will be built actually in several months. So now we have these experiments, we have the materials in their environment, in the electrochemical cells perhaps, and then now what we can learn. So first of all, we heavily use XRD. So because if you look at the peaks, and if you have many of them, which the high energy probe allows you to do, then you can look at the peak position, which gives you the global strains, the compositions, and stuff like this, and the peak broadening, so which comes from the crystallite size and microstrains mainly, right? And those are very important parameters if we talk about electrocatalysis, right? So if we talk, for example, in the battery world, so we look at the lithiation of electrodes, then we look more in the peak positions, where they of course move as you change the lattice parameters due to the intercalation. The data collection is typically tailored for each sample and structural questions. So we don't have really like given way, exactly algorithmic way how we do everything, every experiment, but we have to devise the workflow for more or less for each experiment. The other approach we use is to take the diffraction pattern and do the Fourier transform, which is called pair distribution function analysis. And this is very handy for amorphous materials like electrolytes, right, or amorphous electrodes and stuff like this. And what we also heavily use is the small angle X-ray scattering. So this gives you some idea about the morphology. So now, because lots of the materials at the electrode level is actually at like nanometer scale or tens of nanometers, even at high energies, if you put your detector far enough, you can actually measure these characteristic distances, which corresponds to the actual characteristic distances in the electrode. We are not, of course, instrument which can go like ultra small angles and stuff like this, but for complementary analysis, it's often just enough. And then we can take both those two techniques and we actually combine them in tomography, right? This is something which we call scattering tomography, which was pioneered here at the ID15A beamline of ESRF. And what you pretty much do, you take a pencil beam. So now the new Synchrotron, the EBS source, is really handy in this respect because we have really small beams. And then you scan through the sample and while you're also changing the angles. And this gives you diffraction patterns which are taken in transmission, and they're actually sum of diffraction pattern from sub-volumes of the sample you are probing. So you can do the standard tomographic reconstruction for each Q value of your diffraction pattern you measured, and you can reconstruct the diffraction pattern in the volume of your material. So now we're talking about spatially resolved X-ray diffraction or small angle scattering. I will show you the examples right now, right? So we start with the batteries. And then I will give you many examples so you have an idea how we use these techniques to study the materials and the devices. So batteries, even though it looks simple, and some would even say that it's quite simple thing to do. Chemically, it's actually very complicated, and it's not that we don't know the theoretical, let's say, performance which we could achieve, but we are not able to actually even get close to the theoretical performances. And why is that? Because the battery is full system. It's not just one material, right? So here, for example, here we are talking about the anode side, right? So you have graphite anode, the lithium intercalates in and out. As it intercalates, right? It's at very low potentials. That means that the electrolytes are not stable. So you make these interfaces. The interfaces, on the other hand, might not be perfect, and they can destabilize the whole structure, right? Or they can actually inhibit the flow of the lithium ions inside. So you have to really engineer carefully these interfaces. And as you lithiate and delithiate, you can imagine that there's lots of stress induced in the material, which then leads to the cracking and the lamination and all sorts of degradation phenomena. Then, of course, the ions move through the electrolyte. So the ions can move, or they can grow dendrites. If they grow dendrites and you short the battery, then your bus, which runs on the batteries, will explode. Right? This is something which we want to avoid. So you have to really design well the electrolytes. It doesn't happen. Same as the STIs. And then on the cathode side, it's the same problem. So now it's not only in the real world, it's not only about the actual performance of the material, it's also the longevity. If you make super performant material, but you can charge it only twice, it's probably not ideal for using it in the car, where you expect that the car will be charged thousands of times. So now let's focus on the cathode materials. So cathodes are typically some transition metal oxides, which have the quite large size of the nanoparticles, and the crystalline structure is the key there because it allows the intercalation and the intercalation from the material. Right? So ideally what you want to do if you have let's say micron size crystallite of cathode material, that you fully lithiate it and you fully dilithiate it when you want. But this is very difficult because now you're limited by certain phenomena inside the actual crystallite. So, for example, the defects can hinder the diffusion of lithium inside the crystallite. And of course, if that happens, then you will be never able to use the full volume of the particle. So to understand all these phenomena and the degradation, then we need characterization with chemical and structural contrast, which are able to follow, for example, the defect evolution. So, and the phase transformations during the charge and discharge. So this I'm showing you here. So it's lithium manganese nickel oxide. So those are these high performance, high potential materials, which are not yet in the actual batteries you can buy in the store, I think. But of course, we study them and we see how it goes, right? So now what you can see here in this top, those are plotted the diffraction pattern in the Q range, so within the one diffraction peak of this material, right? And as we charge, so the time goes up here, and we charge, and we see that the position of the peak is changing. So we discharge the material, right? So we actually charge the battery. So we discharge the material, and the peak position changes to higher Q value. That means that the lattice parameter shrinks. This is not surprising. If you take something which was lithium, which was intercalated in the material, and you take it out, your structure starts to collapse. So here at the beginning of this discharge, on this discharge, you see this very continuous transition. So we say that it's kind of solid solution-like transition, where you just take lithium, it gets a little bit smaller, the lattice parameter, and so on. And suddenly you have this jump, right? So this is the phase transition. So now suddenly the whole structure of the unit cell changes. You took one lithium atom out and everything collapsed much more, okay? So those are the important ones, right? And then nothing really changes for a while here. And then once we hit the potential to really high value, then that would mean the full deletion of the battery. There is a very severe transition, right? And this is kind of reproducible. What it turns out is that if you're in this region, this is where the material cracks and disintegrates. So when you charge your battery only to this part, it's much more stable, but you are losing the capacity. So this tells you one thing, right? If you have your cell phone battery or your car battery, don't charge it fully or discharge it fully, because you are starting to go through these phase transitions, which are really detrimental for the battery. The second thing which you learn from this is that there is no free lunch, right? So the future doesn't look like we're gonna have batteries which goes from here to Oslo, on one charge, but we gonna have perhaps batteries which go only 200, 300 kilometers in time, maybe 500, but they will last you the full lifetime of the car. Okay. Now we can look at the same material with a very small beam. This is done at IDO1, right? So beamline. So we take a scanning X-ray nanobeam and we actually just scan through one nanoparticle and we look exactly at the same material, exactly at the same phenomena. So now, this is a little bit complicated here, but not that much, right? So if you look at the lattice, the lattice parameter, average lattice parameter of the whole nanoparticle, then you see that again, this corresponds to that general X-ray diffraction experiment, which we done on ensemble of crystallites. And this is just one crystallite, but it follows in general the same trend. But if you zoom in a little bit, that you find out that actually within the crystallites, there are really regions which are more charged and are less charged. So the charge distribution is quite inhomogeneous. And now the question is, right? So if you are able to, even though it's originally homogeneous, but you keep the inhomogeneity, then you keep the stress levels similar in all parts of the particle, and it would actually be more stable. So this is what we do in this experiment. So here is the charge curve, right? So we have the capacity, this is the voltage. It corresponds exactly what I showed you before, right? So we're looking here, there was this, first plot kind of linear region where there's this solid solution transition. And we can see that if we go from, now we have the strain fields for the particle at each different charge state, okay? And we can see that the strain field actually is pretty much the same if we're in the solid solution kind of region, right? Until right here. Okay, so now we have to go at the bottom, where we actually suddenly see quite a change. From here to here, there is a change in the strain field. This is when we went to this first discontinuity transition, right? And this is where it's already detrimental. And if we go through another one, the particle actually completely disappeared from our field of view, because now the lattice parameter changed so much that we lost it from the detector. It just moved, the diffraction spot moved somewhere out, from the detector, so we don't see it anymore, right? So, and this is kind of analysis you can do within the one nanoparticle. So in those combined experiments, which I show you, you just have the overall information from ensemble of the nanoparticle, and then we understand the actual bulk behavior of the nanoparticles. It's very important to understand the longevity of the material and how they degrade. We can look at the anode materials. So now we have the experiment, where we went in, and then now we are looking at the anode, which is typically graphite, And now we're toying with these composite electrodes, which is graphite mixed with silicon. Why silicon? Silicon has much higher capacity for lithium, but it has also much higher volume expansion. So that means that the particles disintegrate much, much faster than graphite. So theoretically, it's much better. Practically, not really. So we are mixing those two materials with also some other stuff to try to make it stable while we still take advantage of the, the high capacity of silicon. So now you can see that here we charge the material here, right? Little bit. So we're charging the battery. We're moving the lithium in. Then we do the measurement, right? Then we move more lithium in. Then we do the measurement, lithium out, discharge, discharge, and again charge. And again, we can look at the actual interatomic distance in the XRD pattern of the graphene sheets, because this is where the lithium intercalates in between the graphene sheets and graphite. And this is the typical experiment. You know, there's nothing really fancy, so you can distinguish few different position of this graphite peak, right, which correspond to either full lithiation, like lithium C6, or partially lithiated, so it's lithium C12, or fully delithiated, which is here, right? And as you go, as you charge and discharge, this peak, the ratio of the peaks kind of changes, and the peak moves around a bit. What's interesting, we found that if we actually combine with the small angle scattering, then we can look at the size of the domains of the silicon. And the silicon has exactly the domains in the range which we can measure. Therefore, we can see that the domains kind of grow because it's getting the interfaces and the sizes are getting to the point where we can nicely see them if we lithiate the material. So we can follow at the same time the XRD and the SAXS. One is for graphite lithiation and the other one is for the SAXS. So in general, what we find typically in these materials that it's much more complicated system because there is also chemical potentials in between the graphite, lithiated graphite, and lithiated silicon. So even though, and this is you can see it here in this potential curve, even though you do nothing, there is still movement in between these domains of graphite and silicon, and movement of lithium, which really changes the whole electrochemical potential in the material. So, and this is important because this gives you the idea how you should charge your battery, how fast, right? And how, if maybe the best charging procedure is actually to charge it half, wait, and charge the rest. And now we're getting into this electrode level, right? So this is kind of a coin cell. We have it in like assembled in this with what we so-called Sledgelock cells, right? And then we do the same experiment. Actually, when we did nothing here, then we were measuring actually this tomography. So now we can measure the tomography in the XRD mode and in the SAXS mode, and we can compare them. So each of these pixels, right here, voxels, sorry, on this image is one XRD pattern. And for each one XRD pattern, which is maybe 40, 50,000 for this image, we just take the region of the graphite and we look at the positions of the peak and we make these color maps, which then tells you the charge state of the electrode. With the SAXS, we do the same. And now if you compare, for example, here, right, so it's a slice through the electrode, then you can see that the actually when the graphite is getting discharged, the actual silicon still stays charged. So there is also like sequential charging. You first charge the graphite and the silicon, and then you first discharge the graphite and the silicon. I think it's like this. Right? And then you can also see that, for example, on the side of the batteries, which is close to the walls here, the graphite doesn't charge at all, while silicon still does, right? So you first do the silicon, then graphite, and then graphite and silicon, like this. So that's it. That's important, right? So once you are into the cell design, then you have to think about those things a lot. So this is something about the electrolytes. I will skip this for now. So we can measure the electrolytes with the small angle scattering as well. We work a lot in the industrial problems, right? So we are working with, as a part of the TSMAT project. So for the CRF, that's a Fiat research center, right? They want to use the batteries in their new cars. For example, the Genesing, they're making the electrode collectors it's copper plated on some polymer, right? We are working with Toyota to look at the lithium dendrite growth, and we are, for example, working with UNESCO, that's a Ukrainian company who make supercapacitors. And this, so you can use actually, these techniques are so simple, or so simple enough that you can use it to really industrial research. So that's interesting. So now we're really, getting into the realm of helping make the devices, right? So now I'm gonna talk a little bit about the fossil fuels itself, because one of the part of the circular economy is to actually catch the CO2 and use it to make some value-added products. That means chemicals or fuels, artificial fuels. So this is perfectly doable, right? And I'll show you how to do it and how we study these processes. And it's really a part of the of the whole idea of recycling, right? Because this is like CO2 is actually perfect molecule to use as a feedstock, right? It has oxygen and it's carbon, important one, and it's a gas. So first of all, you have to, if you burn fossil fuels, you have to capture the CO2, right? So how we look at these kind of processes. I'll give you an example where we capture the CO2 in the form of carbonate in magnesium. So in this case, magnesium carbonate. It turns out that you can actually really improve this process if you put molten salt on top of it. So you take, for example, some nitrate, I think sodium nitrate, or in this case, or calcium nitrate. And then this really helps actually sequester the CO2 into the carbonate. So why is that? Okay, so we use our typical approach. We just couple a few techniques. We take a little bit more of the modal system. So we take really one flat wafer of what is magnesium oxide, and then on top we put the magnesium carbonate. We put what is this? Sodium nitrate, right? There's a molten salt, and we couple the XR reflectivity, so it's also scattering technique, which you can look at the profile, electronic profiles across the interface, and then wide angle scattering, so XRD. So now this is the typical reflectivity curves, and what you can see here that actually depending on the conditions, if it's the magnesium oxide in helium on the CO2, or there is sodium nitrate on top of it, the shape changes. And the shape tells you something about the interface between the material and, let's say, the carbonate salt. And we can reconstruct from these curves, we can reconstruct the densities of the material. So now we can see that, okay, when we have just magnesium oxide, and then we put it in helium, we have some, let's say, interface here, which is some different density magnesium oxide. When we put it actually into the CO2, we make a little bit of a little bit of carbonate, right, here, but not really into the bulk. And then if we have the sodium salt now in the helium, the interface looks more or less similar as here. If maybe the oxide is slightly thicker. And once we put the actual molten salt on top of it, the interface is super smeared out. So now we really zoom in the CO2 and make lots of carbonate, okay, at these conditions. We can also look at the wide angle scattering, and you can see these rings, which are actually little, so the spots are clustered around certain directions. So this means that it's epitaxial. So whatever we have single crystal, right? Whatever grows on top which is in this space carbonate, is actually epitaxial. And now it's important to this multimodal approach, because from this you have just part of the information. And now you have to go to different facility, and this is really the strength of the relay, right? And then you look at the SEM image, okay, high resolution SEM image. And what you can find that, okay, you have this nice flower-like kind of carbonate features, and around you have these holes, this pitting. And these holes, this pitting is not actually there without the molten salt. So what the molten salt actually does is very simple. It etches the surface. Then you have the magnesium and the oxygen in the, as a precursor, which then helps to form the carbonate. So it's really like this, sequential. You have to etch the surface to get the magnesium and oxygen out to be able to sequester much more CO2. So that's the trick, what the nature does for us. And now, so we somehow can sequester this. We can also catch it, right? So I'm not talking about the catching. And we can look how to turn it into the fuel, the CO2. So the famous CO2 reduction kind of approaches. You use very similar device as a fuel cell for this. And the idea is that you grab the CO2 from the industry, transportation, all sorts of sources. And then you feed it into your electrochemical device, and out goes chemicals. So chemical feedstocks or fuels. You have to supply with the energy. So this is exactly the process which the nature does for us for a million years. And then it, then fortunately, it can store it underground. And that's the underground storage in fossil fuels, what we're using. This is just hyped up version which we developed to do the same thing. So for this, we make a little electrolyzer cell. So now we are really interested to look how to make the high performance device, which can really get to the point that it makes sense to turn this process into industrial scale. So we have this nice cell we developed, right, where inside are these flow fields where you can put your MEA, so membrane electrode assembly, right? Then in the cathode part, you feed the CO2 and comes out your product. And on the anode part, you just feed the anolyte and the anolyte plus CO2 plus oxygen comes out, right? Then you have two catalyst layer. Anode is iridium dioxide and cathode is copper, right? And then this is what you measure here, right? Are those rings. So this is the diffraction pattern. It seems complicated, but turns out it's actually not that much complicated, right? And you can still distinguish different parts of the cell and different materials inside. So now we run the electrolyzer, and then we look at the product, which is a TV, and then we just kind of look, and interestingly, if you look at the product, you see that it just drops, and at the same time, the hydrogen goes up, and then again goes up, and the hydrogen goes down. This is very interesting, right? This we don't see in the fuel cells in the hydrogen conversion system, which I probably won't have time to talk about, but doesn't matter. So what's really causing this? So you look at the diffraction pattern, and one of the feature is that, of course, we are changing here. This is some kind of subtracted and in log scale. Don't pay too much attention to this, but what's really changing here is the background, right? So the background is important in this kind of experiment. Background is typically your electrolyte or water. So there is movement of the anolyte through the membrane onto the cathode side, right? So, and now we can actually, looking at the diffraction pattern, we can look at the water distribution in the cell as a function of applied current. And this is exactly this curve, right? And we can see that, and this is the distribution. This is in x-axis, you see the time in the middle, right? And the y-axis, you see the position of the cell. And what you can see that, if you look at the oscillations, they perfectly correlate in some kind of water buildup in your cell. So why the water should build up there, and where does it come from? It turns out that it's actually much more complicated. It's not only correlated to the electrolyte buildup, but also the formation of the carbonate salts on the cathode side. And then once you put, and this is, this is what you have to do if you want to understand the phenomena at the device level. You have to measure all sorts of stuff at, at different conditions. And what you can come up with is actually very interesting phenomena, right? Where you have this oscillating behavior, which is really like where the full cell and everything kind of works together to make those oscillations. So first, let's start that we decrease the water content in the gas diffusion layer. Then we form the crystals of carbonate. This blocks the CO2 stream on the electrode, which in turn increases the hydrogen evolution. This is what we saw there. That means that the membrane transfer favors hydroxyl groups. Then this means that the potential decreases also in the cell. This increases the flux to the cathode. This means that the cathode GDE starts to flood, right? Then the salt gets dissolved. Then the CO2 accessibility increases. Then the CO2 reduction increases. You see the now increase of your product. Then this membrane fibers the carbonate transfer again, potential increase, water decreases flux, and it keeps going like this. So this is important, right? Because this really slows down your performance of the cell. I think I don't have too much time to talk about the hydrogen, so I'll skip this. I wanted to talk about it more, but I think you got the idea. It's very similar, right? What we do here with the CO2. Let me summarize this. Using high energies is really good, especially if you go to the level of the conversion device and bulk of the materials. And this is really advantageous for in situ and operando electrochemical experiments because you don't need to compromise on the cell design and you can really study high performance devices. XRD can be taken to different levels, so that's something which should be always taken into account, that in XRD there is much more information than people typically analyze. Then the other kind of thing which is good to keep in mind, that we can couple the XRD and SAXS and in general elastic scattering with tomography, which opens a large opportunities if you want to understand now some spatial distributions and spatial phenomena. Now what is next? Of course, there is the holistic understanding. This is for me is the goal to understand fully the materials at the device level, how they work together and what to improve not only in the single material level, but also how to put them together and how to run them. So optimization. Then we can move to definitely larger devices. And we can also are getting to the point where we can have true single nano-object characterization with coherent beams. I didn't talk about it too much, right? And this is the EBS kind of. So now with the new source, we can definitely hype up the multi-scale operando for characterization because we have smaller beams, more coherent beams, and we measure much faster, right? This gives us the access to fast 3D visualization. We can also almost access the timescales of electron transfer, right? At some of our beamlines. We can couple chemical and microstructural operando measurements. We can get subparticle information. I showed you one example. And we can also simultaneously measure complementary low-Z and high-Z values with X-ray Raman. And I would like to finish it here. And thank you for your attention.
For this very exhaustive presentation. You went really like from fundamental to industrial applications. So it was really interesting. We can wait a few seconds to see if we have questions in the question and answer chat. So if you have any question, please use this tool for writing your questions and we will report them to Jakub, or Jakub can see them directly. We give time for people to answer to see the to write a bit the questions. In the meantime, can I ask you, like, how do you foresee the ESRF to be used by the remade, like for really fundamental questions, or rather for more industrial application? What do you think that how do you think that ESRF will be used by the remade users?
So ESRF, there are quite few instruments which are involved in remade from ESRF side. So we have, I talk about the diffraction, right? So this is a tool which is really good from the fundamental perspective. So you can use it for the fundamental studies. And I showed you that it's possible to use it all the way to the industrial problems, right? And that's the beauty of the high energies. We also have, other part of the remade, which is more focused on the imaging, right? So this is the true absorption tomography and imaging of fast processes. So for example, that kind of tools are really handy if you want to optimize certain industrial processes or optimize the materials, understand the morphology of the materials, how they change, right? So I think that, I think there is a really broad spectrum which we can offer at ESRF for the remade projects. So and it's really up to the individual researchers and what's in the project, what would be the most appropriate approach.
And just to give a bit of an example to users, when they apply for beam time at ESRF, what are reasonable amount of time that they can ask for? Are we talking about hours, weeks?
So that very much depends what is the problem in hand, right? So if you are thinking about doing operando experiment, that's probably that's very within the realm of days. Let's say if you want to characterize single material, or you want to do some high throughput measurements, that's probably like matter of 1 day, right? But I think like like up to 3-4 days, it's reasonable time for complicated experiments to be performed at ESRF beamlines.
Thanks a lot, Jakub. I don't see any question popping out, but I encourage the viewer of this video, if they have any question specific to diffraction problems, they can write to Jakub and he can guide you directly. Jakub, can I share my screen for the final remarks? In the meantime, we can still see if there are questions.
Wait a minute. Post share. Stop share. Perfect. Go ahead.
Okay, perfect. Thanks a lot. Okay, so this is this one. So we ask the viewers to give us feedback because we want to improve our webinar series. So if you want to help us, please follow this link. It's a very short survey. It will only take few minutes, but you can help us help you. So if we can target better what are your needs, what are your requirements for this kind of series, please follow the link and give us some feedback. I also want to remind you the next presentation, which will be roughly in a month, 19th of May, same time, same place, 2 p.m. on Zoom or YouTube. We will have an introduction to small angle neutron scattering from Sarah Rogers from ISIS Neutron and Muon Science. And as a reminder, you find all the information on this webinar series on the website, where you also find all the information about the technique that Remade is offering and who you can contact. So thank you all for your,
Okay, Marta, there was a question, there was a question.
Go ahead.
So, could you actually run, Julio asks, could you actually run an operando XRD measurement in battery in normal diffractometer? Yes, you can. It's but you have to have source which goes sufficiently high energy. So copper alpha, it will be very challenging. But I think there are some point cells where you can maybe do this, but I'm not 100% sure. but this is this can be done. Okay.
That's perfect. Thank you a lot for the questions. And again, if you have any questions in the coming days, I know that sometimes they come like during the night. The remade, so we like you find the contacts from from different techniques in the website on the remade project.eu website. You can contact directly the person that are involved on the specific infrastructure or technique. You can contact the general, let's say, remade project staff, and we will help you to find out what is the best technique for your specific problem. So I think that's all for today. We are perfectly on time. I wish you all a pleasant weekend, and we'll see in a month for the next seminar.